Welcome everyone to the first webinar that we are doing from AI for Maths. We are starting this series of webinars where we will be discussing different topics related to the meeting and collaboration between the medical field and the field of AI. The potential that this moment has now with the collaboration between these two fields, ongoing projects that are happening, and many other things. But to start, we thought that given the huge impact that large language models have had in these last few months, it would be very interesting that if this first webinar was about how these models can actually be used in the biomedical field. And so the idea is just to give a brief introduction to the field of natural language processing that involves these large language models. We are not going to get very much into technical details, but we will also see its application in the biomedical field. And finally, we will show a bit, and probably the most interesting part, like how one can play around with these models. And if we can actually say it, how can one talk with these models? So let's get into it. So basically the agenda for today, first I will introduce the field of natural language processing. Then we will move into this large language models boom, because we know that these last months, everyone has been talking about the large language models and what they are capable of. But we're going to see how is it actually in numbers. Then we will see how these language models can be applied in the biomedical field. And as I said, the last part will be how can one talk with these biomedical language models. And then I will show you like some websites or some resources that you can use and that we will also share with you afterwards, so you can play around yourselves. But so what is the field of natural language processing, or what are we talking when we say natural language processing? Basically, let's take it by steps. Natural language is broadly a term that refers to any kind of language that humans use for communication and that occurs naturally in a community, in a human community. As it can be, a simple example is like English. But so when we move into the natural language processing is where like computer science and linguistics, these two fields, try to find the way to automatically generate and understand natural language processing by the computer, so that we are able to communicate to computers in a natural language. So we're able to talk English or write English, and the computer, which normally works with zeros and ones, is able to understand what we're saying and can actually also reply in a natural language. So how can we actually do this talking with computers? And the basic idea is to use these language models. But basically, the idea of language models is simply models that assign probabilities to sequences of words. And those were introduced by Claude Shannon in 1948 with the most simple model that has been developed for like natural language processing, which is the n-gram, which basically assumes that this natural language is an stochastic process. So if we think about the process of talking, how we talk, usually you need some context from what you've been saying before to kind of know what word comes next. So basically what Claude Shannon said is like, this is an stochastic process that you can assign probability, and then you can get like the whole meaning. But so the great advantage from this model, the n-gram model, is that you don't need to know the whole history, but you can approximate it by just focusing on the last few words. So basically what he was doing is like assigning probabilities to the sequences of words based on like the close words to the one that you need to say at that point. So basically the outcome from his paper is that he found out that it appears then that a sufficiently complex stochastic process, which is simply giving probabilities like to random processes, will give a satisfactory representation of a discrete source. So like that we can talk. So giving random probabilities to this random process of creating words, we will be able to create an understanding language. But to make it clearer, let's just go into an example. Let's imagine that we want to describe this sentence of like, I love eating pizza every day. And for that, we will use a very simple model, like the n-gram model that's used the b-gram. So we will, every time we want to generate a new word, we will just pay attention to the word that was before that one. So let's start with this bigram example. Imagine we start with the word I, and then what this model would do is like, we need to find the probability of the second word given the word I, so the first word. And then we would have to go through all the words in the English language, and we would be able, based on like how the language is used and how the model has learned to produce these probabilities, to get the specific word. So in this case, like the highest probability would come from the word love. And then so we would put the word love, and then this process will keep going on. So now we would need to predict the word number 3 based on love. So given the stochastic process of generating the English language, we would guess a new word, which would be eating, and then we would do the same for pizza and then every day. So this is how it would work. But usually this is a very simple model. Usually we need a bit more of context, and then we would work with like trigram or bigger models where they pay attention to more words in the past. But so basically, just to very quickly go through the history of the natural language processing, as I said, we started in 1948 with the Ngram model, which is completely independent from AI. So it's purely based on these stochastic processes or random processes from the natural language itself. But then from the 60s to the 80s, we are in what is called the rule-based era. So all the NLP research is based on these complex sets of handwritten rules. So we are just basically they were just basically trying to define rules in the language so that the computer would be able to reply to you based on what you were saying. And here we see a figure of like what is called maybe the first NLP program, which is called ELITHA, that it was developed between 1964 and 1966 at MIT. And here we can see that it's some kind of like a bot. So like the user talks to the computer, and the computer is able to reply in natural language. But as we can see with this rule-based era, it was very hard to really have a fluent conversation, because as soon as the human or like the user exceeded the small knowledge that the model had, this model would only, or like this program would only be able to provide a very generic response or repeat somehow the input that you had given. So here I have given 2 examples where, like, for instance, the user says, well, my boyfriend made me come here. And then since the model did not know actually how to reply, it said, is it important to you that your boyfriend made you come here? So it's in some way just repeating what you said. And then the second example is true, I'm unhappy. And then it just asks, can you explain me what made you unhappy? So it's kind of like not very sophisticated language, but still quite impressive for the times that we're talking about. But then in the 90s, we go more into like the machine learning era. So AI starts appearing and it starts being applied into NLP. But the big jump was in the 2000 and 2010s, when the big data and the deep learning appeared. And those gave like the start to these large language models that we are using nowadays. Just to quickly, not get very technically, but the idea of deep learning is using these neural networks that I'm showing here, where we start with the input layer, where we give the information, and then each point is a neuron that will process the information and will learn in a way to be able to reply to you based on what you're saying. So these like very broad terms, but the idea is like we are training this neuron as if it was like, the idea comes from like the brain, as if it was a brain, and like the different neurons learn to do different processes, so the computer is able to answer to our inputs. But so very quickly, in 2001, this neural network architecture was used in the natural language field. So the first neural network-based language model is proposed. Then, just as a fun fact, in 2010, 2011, if you remember, Siri was released as an app, and Apple integrated it into the iPhones. So we started to be able to talk to our phones, and then they would somehow understand what we were saying and also reply to us in English or any other language that it was used for CD. A very huge technical improvement was in 2013 with this Word to Back, which was a publication because we're saying you cannot actually talk to the computer in a natural language way, but it works with 0 and 1s. So what these word embeddings do is they define in an n-dimensional space, so in a very big space, you have each word represented as a vector. But so the idea for you here is a representation in a 3D, but the idea is like each point is a word, and the closer the words are in this 3D space, the closer is its meaning. So we kind of find a representation of the words that a computer can process, and there's a meaning in where they fall into this space. And just to give you an example, I did some zoom into this 3D representation, and here we can see that all the terms that fall together are somehow related to each other. So this is very powerful in order to be able to talk to the computer. And then finally, I will definitely not go into detail with this, but in 2015 and 2017, the whole attention mechanism and the paper of attention is all you need came out. And here I'm showing like the transformer architecture that comes from this 2017 paper that revolutionized the field of NLP and made us go into like very quickly, as we can see, like in 6 years, we've made a huge advancement in the field thanks to this type of architecture. But so now is the era of the large language models. Boom. So we know that in these last few months, even like people that were not related to the field started to hear about ChatGPT and all like these bots that you can actually talk, and they like they really seem humans, that it really seems that they understand what you're saying, and they are actually able to give you a really good answer. And what I'm showing here, the idea of when a language model becomes large is based on the number of parameters, or like the number of neurons. If you remember from the graph that I showed before, in their neural network, the number of neurons that are part of this model. So what I show here is these last 5 years, how the dimension of these models has increased. So in 2018, we were talking about way less than 1 million neurons or 1 million parameters. But then very quickly now in 2023, with the GPT-4, we are talking about 1.7 trillion parameters. And you know, when you talk about these very big numbers, you might kind of lose the context. So what I did is ask ChatGPT if it could give me an impressive metaphor of how much 1 trillion are. And it said, certainly, imagine 1.7 trillion as the number of heartbeats it would be take for every human on Earth to collectively beat their heart for over 200 years. So now we can have an idea of how much, or like how many 1.7 trillion parameters are in terms of like the number itself. And so that's also why training these models has become way more expensive and way more time consuming, because it's a lot of parameters that you need to play with to get like the optimal performance. And here's just the second plot or graph of the different models that have been developed. We can see like a lot of research centers, scientific groups, or like even private companies are developing more and more language models. This is only here where I'm highlighting is from 2021 to 2023. And we can see like the sizes are huge for some of them, but still like there are a lot of models being developed overall. But so why can it be interesting to apply these large language models in the biomedical field, or actually what is it when we talk about language models in the biomedical field? So it's basically language models that are trained on biomedical data for various biomedical tasks. So when we talk about biomedical data, like it's a broad range of data. We can go from the clinical and registered data as like the electronic health records or your clinical history. You can train language models to understand and get a context of your clinical history and maybe kind of make predictions of your future outcomes or how you're going to react to certain drugs. or it's going to be able to taking your whole clinical history to quickly make a summary to the doctors, so they don't need to go and check everything themselves, but like very quickly they get an idea, an overview of your clinical history. But then we can also go to more biological data per se, kind of like genetics. So we can have models that are trained on DNA sequences, protein sequences. We can also train it on brain imaging. So we kind of can introduce a lot of biomedical data into the language models, and then they can be trained to do a lot of different biomedical tasks. And so people realized about it, and so they started publishing a lot of different papers: BioBird, Clinical, AlexNet, MedGPT, BioGPT. So it has been quite difficult to have an overview of everything that's going on. And so today, what I will use is this systematic review or the systematic survey that they went through the language models in the biomedical domain to kind of get a general overview in the field. So basically, first of all, why do we want to apply language models in the biomedical domain? The idea is like annotated data in the biomedical field is usually not large scale. So when we talk about machine learning, usually in very broad terms, you need to have annotated data. So you need to tell the model what it should actually predict, either like a 1 or a 0, or which class should it predict. But this deep learning allows the introduction of just big data into the model, and the model will figure it out itself and in an unsupervised way, the patterns that it sees in the data. So the fact that the biomedical data is mostly unannotated means that these language models should be very good for processing this data. Secondly, is that the biomedical domain is very knowledge intensive. So there's a lot of technical information, and usually it's very specific what we have in this field, way more than the general domain. So these models, large language models, applied in biomedical data instead of like the general website, as models like GPT, like BERT has been trained on, it should be easier to capture or like to find the things that the model should pay more attention to. And then finally, as I said, this large scale annotated biomedical corpora and biomedical sequences is very difficult to handle, not only in like in terms if it's annotated or not, but it's this this big data, this big bio data. There are no other models that presumably could predict and make good predictions, or could be good applications for this field. And so these models should also be really good at handling this kind of data. And so here what they just show is a timeline, chronological timeline, where you can see the language, like the biomedical language models at the top. And then we see that first the general domain language model was published, and then few months or years later, the corresponding biomedical specific model also appear. So this is an ongoing thing in the scientific field. That is just when you publish the general domain, like another research group or the same research group trains on specific biomedical data, and then you can publish your more specific model for the biomedical domain. And so in the systematic review that we're using, they went through all these different models. We will not go into detail, but I'll just talk about some very few examples where, for instance, we have BioGPT, which is the one that we will be playing with today, where like mainly they use this GPT architecture. I will not go into detail, but there are mostly two main architectures, BERT and GPT. But GPT is more, it's easier for this model to generate text. And so basically this model was trained on biomedical literature. So it's like 15 million PubMed items, which is like the title and the abstract of 15 million PubMed publications. Then we have the clinical BERT, which is like another example of like the BERT-like architecture. And this one was trained on clinical text from 2 million notes from the Mimic3 database, which for those that are not familiar with this database, is simply a publicly available database with clinical information, including clinical notes. And then finally, we have the MedGPT, which is the GPT architecture trained on patient's medical history. So basically, it is more the current electronic health records where you have all your clinical history. And the idea is like, as I said before, if you give the past events that happened to you in a sequenced way, this model should be able to predict future events, such as diagnoses that you may have, or if you already have some diagnoses or some complications, how it would evolve for you based on your clinical history. But we also have uses in like the private sector. We have this Dragon model used from Nuance, which they claim is the next level speech-driven clinical documentation. So basically, the idea is like the doctors won't have to use any more time to type the clinical notes, but they just need to talk to the computer, and the computer will create structured clinical documentation. And we also have Cordy AI, which is a company that is trained on thousands of hours of real patient calls. And then this company was listening to these calls and was trying to make it into an actionable insight and suggestion. So like in a way to avoid having humans listening to the calls, but having some kind of AI intelligence that can process your data to faster send you to the professional that you need. So what they claim is that 46% more clinical emergencies were identified in the Copenhagen Emergency Medical Service. But so we also see that there are some applications out there in the private sector. But what they also realized in this systematic review is that, of course, there are some limitations and concerns. First of all, they said it is true. These biomedical large language models always showed to have a better performance than general text models for this biomedical task. But we need to be careful with these large language models. First, in the biomedical field, but also sometimes in general. The first one is the misinformation. So, for example, the electronic health records can contain wrong information, either because there are some issues with the data processing, or because maybe sometimes the doctors don't have a lot of time to make the data introduction, and then some fields might be missing. Maybe sometimes the diagnosis codes might change over time. So there might be a lot of misinformation or misclassifications that we will be giving to the models. So, and we need to be very careful with this because we know that the grounds of these AI language models is to find patterns on the data. So if your data is wrong, definitely this model will not perform well. But what they suggest is like the predictions should be always calibrated by biomedical experts before they are actually implemented or used by the end users. We can also have interpretation issues, and we know this is very relevant in the medical field because we don't only want to get a prediction and like from this kind of black box model where you input the data and you get the output, but you don't really know what's going on inside the model, but you want this more glass box model where you kind of want to see the reasons that drove the model to take those predictions. So what they say is like it would be very great for these models to provide some reason, and if it can be textual, it would be even better for the predictions, both for clinicians and patients, because it would be very nice for like the medical doctors to get an explanation, both for themselves to see if it makes sense or not, the prediction that the model is doing, but also to kind of communicate to the patient, so to make easier the communication process. Of course, and as usual, there's also the ethics and bias that's over the whole AI field. We need to make sure that the decisions that are made by these models do not reflect any discriminatory or biased behavior towards specific groups, such as like maybe in terms of sex, in terms of ethnicity, in terms of age. So we really need to make sure that this model is super unbiased. And I know there are a lot of or like few research groups out there working with this and trying to make sure that we define some processes to discover how biased our model might be. Then finally, it's also the privacy, of course, is very relevant. We know that it's very important to follow different regulations to, kind of like respect the privacy in terms of like data from the patients, because it's very sensitive information that you have in the clinical records. So we really need to make sure that when we introduce this data into the models, it's de-identified and it is very safe. And there's no way that the model or like other people can pick up this information, especially because some recent studies have shown that there might be some data leakage from the pre-trained models when you are using it. So it is possible that if you, during the training of your model, include sensitive or personal information, that somehow when you give that to the end user could actually retrieve some of this personal information from your patients. So you really need to make sure that the privacy of the patients is safe. And the last one is this trade-off between the coverage and quality, which kind of relates to the first one that we had. So we have these very large electronic health records, but we really need to make sure that the quality of the data in there is correct. So we want to have this big data. So we want to give a lot of data into the model because they actually need a lot of data to find patterns. But that doesn't need to mean that the quality of the data is very low. So we always need to find the trade-off or the equilibrium between these two. But so now that was the finish, like the end of the presentation. You are more than welcome to send any kind of questions. You can follow us on our different social media. And now we're going to move on to how can we talk to these fields. Because my area of research, I'm currently working, I'm a PhD student in Copenhagen, and I'm working with the Danish electronic health records. And we're also trying to figure out, okay, how can we use these models to use in the electronic health records and to kind of get some predictions for psychiatry. And so one of the best resources that are currently out there is Hugging Face. I will talk more into detail later, but Hugging Face provides a lot of different models because sometimes training these models might be very expensive and very time consuming. And maybe if you don't have the data, it's also not doable. But Hugging Face allows any type of user with more or less programming knowledge to have access to these models, data sets, etc., etc. And then usually, and which we will also use today, if you want to talk to these models, you also need to use Google Colab, because, as I said, these models might get very, very big, and probably most of us don't have computers powerful enough to run these models in our own hardware. So we usually need to use this Google Colab. But so when we talk about Hugging Face, is this private company and open source community that is really making like huge contributions to democratizing AI tools, especially in NLP. So giving to the open source community, like end users, anyone that wants to play around with these models, the opportunity to do so. So as I said, you can find the models. And when we say models, it's like the weights or the different values that we need to put into the neurons for the model to work. So we can download those. We can have data sets like clinical data sets, because many people might not be able to have access to these data sets. And then also computational power to deploy your models in case you want to publish or deploy your models there. Or like you can also somehow, to some extent, play with the models in their website. And then for Google Colab, this is Google Collaboratory. It's a cloud-based service that's provided by Google, and it gives free access to everyone to computing resources like GPUs, CPUs, and TPUs. Just by having your Google account, you have access to it. And the main idea or the main focus for this Google Collaborative service is to run Python code in Jupyter notebooks. But so this is what we will be working on today and what also like many people use. So as I said, it's very easily configured. If you have a Google account, you can access the Google Colab, and as soon as you create a notebook or like a file, it will directly be saved in your Google Drive. So you don't need to do nothing for that. And the issue, of course, sometimes you cannot run these models forever, or you cannot have access to infinite compute power. So there are some time and storage limitations. So you cannot run very heavily or highly demanding computations because it will crash, or you would also like run into issues of time. But still, it's like an amazing resource for like the end users or people that cannot access these very powerful machines. So here I'm just giving a few links to the transformers, which is this part of like Hugging Face that we will be focused on, which is focused on NLP. And then the model that we will be playing with today, which is the BioGPT. And then also like the easier implementation that Microsoft did of this model, which is actually the one that we will be using. So this is it for the presentation. I'll stop sharing the presentation, and then we will move to the part of the website. So I'll just share this one here. And so when you go to Hugging Face, you see this like this is their website where you can see like they have models, data sets, all types of documentation. So everything is really well documented. And of course, you can also sometimes pay a bit to get a little bit more computer power to also like deploy your models and stuff. But so it's as any other kind of website. It doesn't look so scary. And so then we go into the transformers, which is kind of like the part of the website that we are mostly focused on for NLP. And the idea is like it provides APIs, tools. So they have in here everything NLP related that you can easily download and like or play around with. So you can have all these large language models that you can and use thanks to Hugging Face. And like here they also have lots of documentations, tutorials, so you can like see what you can do, developer guides. So as I said, like it's extremely well documented. And so I'll just close one. So if we can go into like the BioGPT. So here we can see like at some point there are like the models. Here we have the models, text models, which is the one that we are mostly focused on. And here you can find plenty of models. Today we're focused on the BioGPT, but there are many different models that you can play around with. But so here, this is like the main implementation of BioGPT that comes from this paper that they refer here. And yeah, you can see that here's like more general documentation of what you can do, but then it also gets into like very technical documentation of like the different classes or functions that this implementation has in terms of like if you want to play around with the models in like a more technical way, you can also look for the documentation here. But so today we will focus on the Microsoft implementation, which makes it a little bit easier for the user to play with. Again, they here have some very general numbers and some code example that we will use in our test later, or yeah, I will show you how it's used and I will share with you so you can also play around with. And also the good thing about this implementation is that they also in this API give you some option to directly play with the model here. So for instance, if you introduce COVID-19 and then you try to compute, it would say it's a global pandemic. Here it was already. So if I just erase, it will just give it again, but then you can also change it to any other thing. So you can say like cancer is, and then compute, and it will say is a common cancer in the world. We will talk about it, but we will see that the problem with these not so big implementations, sometimes it's like And we know it also happens with the ChatGPT. Like the answers it gives, it is not perfect. So this field is still evolving. But for instance, like penicillin, and then we can give time can be used as a therapeutic agent for treatment of infections caused by a penicillinase. And you can just come here, but it's like pretty limited what you can do here. So like the interesting part is to go ourselves into Google Colab and play around with different parameters and talk to the model. But I promise it will not be really hard. So if you Google Colab, you will get these different links. Basically, you can come to this second one, and it will show what I explained you before. Like it's a hosted Jupyter Notebook service that requires no setup to use and provides free access to computing resources. So it's very nice for like people that work with machine learning, data science, and education. So like it's very, very cool. And then if you come to the first one, it will quickly relate to your current work. But so if I come here, I already have developed our own notebook for this webinar, and we will show basically all you need to do to talk to BioGPT. But so it's already here. You just need to run the different cells or like execute the code, and you will be able to talk to it. So the first thing that we do is we install some of the different packages that you need to run these models. So transformers, which is like the one we get from Hugging Face, and then Saccharomyces, which is just one that we need to download the models. And then we, from these packages or like these libraries, we get what we need. And so the idea is then to download the model. We can see that it will take some time. But so what we will do is we will download the BioGPT from this Microsoft BioGPT implementation and the tokenizer. I didn't go into detail, but the idea of this tokenizer is that you are not able to talk to the model directly, but this model needs to kind of create tokens from the words that then it will put into the vectors. So it's basically the translation from natural language into language understood by the model. So here you can see it will take some time because the model is like 1.6, 1.5 gigabytes, and like many other things that are going on in the back. And then we will start running this here. So we have the generator. We will create a kind of like a pipeline where we will ask that we want the text generation using the model that we just downloaded up here and the tokenizer that we also just downloaded up here. Set seed is because some parts of these models are based on random initializations or random processes. And by setting the seeds, we make sure that all the results that we will get every time that we run with this seed will be the same. We can just change this number here, and then we will get a slightly different results. But then the idea here is that, as we did before, we can define what's our input text as a cancer ISA, and then we can run our generator. We say like this is the input text, and then we can specify how long do we want our like result sentences or like output sentences to be, and how many return sequences. This is not so relevant. This is just what they recommend to run the model with, but just it's there. You don't need to really pay attention to that. And then we are now actually running the model. So we are giving to the model cancer ISA, and it will produce 3 outputs of maximum length of 50. And so the first one it generated is a disease of the blood. It's an heterogeneous disease which can present with either local or systematic symptoms at presentation, or cause of cancer-related death worldwide, and thus novel strategies for screening and real analysis. And so we can see some of them make more sense than others, but still it's pretty impressive, right, that it can pick up some of these things. Another option that you can use is this kind of like question and answer. You can actually ask, is oral ciprofloxacin useful? And then you can give some kind of context here, like for the model to get some more specific information. And then for the answer to the given question, the answer to the question given the context is, so it knows more or less how it needs to start. I must say that this example here, it's not so useful because as long as you get out of some of the fields that maybe this model has not been trained on, it will give useless or random answers. But here is like the same. We have the input text, the maximum length, and how many sequences. And then the answer that would give comes here, cost savings over our variety of parental, antimicrobial regimens. So in this case, I guess it kind of gives a useful information, but still, this one is not the most useful of the cases. And then here again, we would go for the third example with COVID-19, maximum length 20 and giving 5. So these are just like different ways that you can play around. You just need to change the cans or like the input text. And yeah, you can also choose how long it can be, how many number of sequences. Of course, the longer you choose or the more sequences you ask the model to give you, the longer it will take to get the output. But just so we get an idea, because now we get some output that is very nice and easy to read and like English, but how do this output actually look? And for instance, I tried a new one, which is related to my field. Text the most critical psychiatric diagnoses are, and then we encode the input using this tokenizer. So we kind of like translate the natural language into the language that can be somehow understood by the model. And then we just want to get the output as it is without put it in back into the natural language. And so if we run the model, we see that it's basically yeah, depending on who you talk to, a very ugly matrix of numbers, where each point kind of like represents the probability for the different words that should be coming. But so yeah, this is just to see that there's actually some math going at the back, and the model is basically trained on numbers and not like words, as this might seem. But then some other final application that they recommend from the Microsoft application or like implementation is to use this beam search, which is basically a different way of decoding the sequences. It's like it pays a little bit more attention to the context, so it not just only pays attention to the last word predicted, but to more words. So here the sentence I use is like, how does exercise benefit our overall health? Again, we translate using the tokenizer into an input that the model can use. And then we set the seed to make sure that we always get the same results. And this is like maybe a more technical part, but you just need to like run it again. You don't need to change anything from here. But then you will hear again, like, how's the minimum length and the maximum length on the output that you want. The number of mean beams, which means how many words in the past you want the model to pay attention to or to keep track to make the prediction. And then you just need to decode the output in a way that it's read by us. So you kind of like do the process that you do here to be able to go from words to something that the computer understands. You here decode, so you go backwards kind of. You go back to from numbers to natural language. And here we can see the result. It took 35 seconds to run this time. And instead, the systematic review and meta-analysis of the effects, yeah, with chronic obstructive pulmonary disease. So it's like basically we can see that it's not such a good answer, and you can see that this model was trained on PubMed abstracts. And so it's kind of getting information from these systematic reviews that has found in like the database that it was trained on, and that's how it gives the answer. So we can see that these models still have a lot of limitation, but we need to remember these are still models that we are being able to run as end users and like in this free access computer power that Google is providing. So this is another thing. Sometimes to run this model, it will take more or less because the availability of resources in Google Cloud depends on like how many people are using it, how heavy are the code or the different things that they are running. But so yeah, this is more or less I will provide this notebook to all of you, and you will be able to run it in your own Google Drive, and you will be able to play if you want and change the different input text and like the different parameters and like play around with it. But so also an interesting thing that I wanted to show and to really be aware of how big ChatGPT has been is that we can see that these models actually need some time to run and the output they provide is not that good. But so what would happen if we include this into the ChatGPT and we compare, right, how the different models perform? And we can see that very quickly, ChatGPT starts giving you a very specific and very detailed answer with lots of details. And yeah, I think it's very impressive, and it kind of like makes us be aware of how big ChatGPT has been. Of course, we need to be aware of its limitations and concerns that I commented before, but still, it's very helpful, and it can provide a lot of insight into different fields, and it can kind of give you a very quick overview of what's going on. And yeah, just the fact that we can access to this very easily, and like you just need to create an account and you can get access to these very powerful models, just seems very impressive to me. But anyway, thank you so much for coming to the webinar. Hope you enjoyed it. Just remember it. You will have access. Hopefully we will include the link to this notebook in the social media where we upload the video, which is probably going to be YouTube. And yeah, hope you have fun talking to these models. So thanks for it, and see you at the next webinar. Bye bye.